This is the fourth and final section of the volumes of revolution chapter. This is modelling with volumes of revolution. So there isn't any new content in here. It's just going to be applying what we've learnt about our volumes of revolution. So quite often in these questions you are given measurements in centimetres, so you're going to be working out volumes in terms of maybe centimetres cubed or metres cubed. It may involve things like scale factors as well, so it might be worth mentioning scale factors here. Okay, so remember that if the lengths are increased by a scale factor, so let's say lengths increased or multiplied by a scale factor, okay, what that means is the volume is increased by the scale factor cubed. And if we are dealing with area or surface area, area is increased by the scale factor squared. So those things are often useful. Right, so you've got a goldfish bowl, and this is the parametric equation. There are limits from my value of t, so they can't go outside of that range. X and Y is in centimetres. The bowl is formed by rotating the curve 2 pi around the y-axis to form a solid, and we need to find the volume of water required to fill the bowl to a height of 3 centimetres. So if it's a height of 3 centimetres, that gives a y limit of 3 and a y limit of 0. So since we are doing a volume of revolution around the y-axis for a parametric equation, so let me write down t2 and t1 as my limits, as my t limits. This will be x squared dy dt dt. Right, so let's start with my limits. So with my limits we start with a y value of 3. That needs to go into the y part of the parametric equation, so that's going to go in there. So when I do that, I will get y, or sorry, not y, but 3 equals 2 cos t plus 2. We take 2 away from both sides, so we end up with 2 cos t equals 1. Cos t equals a half. So we do the cos inverse of a half to get my limit of t2. That's the one at the top. So cos inverse of a half gives me a third pi over 3. Okay, so that's my upper limit. So it goes at the top. Then for the other limit, we will do y equals 0. So that becomes 0 equals 2 cos t plus 2. That will be 2 cos t equals minus 2, cos t equals minus 1. So t will be the cos inverse of minus 1, which will give us a t value of, let's do this, pi. Okay, which is my lower limit, so this is t1. Now what else do we need? We need dy dt. So dy dt is going to be, when I differentiate y, so that would be negative 2 sine t, and then the plus 2 disappears, right? So let's highlight that. Right, I'm going to carry on over here like this. So we have pi, limits of pi over 3 at the top and pi at the bottom. Don't be tempted to move the bigger one at the top, because remember, these are t values. These are not values on the axis. So keep them as they are. The y equals 3 is at the top, so the t2 pi over 3 goes at the top. The y equals 0 is at the bottom, so the t1 equals pi goes at the bottom. Then I need to do x squared. So x squared is going to be 4 sine squared t times by negative 2 sine t dt. Right, so we've got a negative 8 as a factor, so that comes across. So pi over 3 pi, and then we've got sine squared t times by sine t. Now I could write this as sine cubed. Yeah, we know that this is actually the same as sine cubed t, but to integrate it, I'd split it back up into sine squared times by sine. This is what we do with odd powers. Yeah, we split it up like this. The reason we do that is because the sine squared t I'm going to replace with 1 minus cos squared t. It's going to enable me to integrate it. So I'll just go over here. So minus 8 pi over 3 pi, and then I'll have 1 minus cos squared t sine t. Now to integrate this, I'm going to use substitution. Yeah, so I want you to focus on this bit, and I'll do the substitution down here. Now in my substitution, I'm going to make u equal to cos t, which means that du dt is minus sine t, which then means that dt is equal to du over minus sine t. Now I'm not going to change the limit, so I'm only focusing on this part here. Let me just highlight it. So I'm not going to write all the integral sign out. I'm just using this to help me integrate. So I could then write my integral as 1 minus, that's going to be u squared, times by sine t. Yeah, this is not trying to integrate. Times by du over sine t, negative sine t. So there's my substitution. Now what happens? That cancels out, and in fact this becomes the integral of well, because we're timesing it by minus 1, it will be u squared minus 1, yeah, du. That's very easy to integrate, so I end up with u cubed over 3, or a third u cubed minus u. Now if I substitute back, I'll end up with a third, and my substitution was cos, so it's cos cubed t minus cos t. So there I have done my integration. So let's go back to this, and this integrated, so I'll have minus 8 pi here, and in brackets I will have 1/3 cos cubed t minus cos t, with limits of pi over 3 and pi. So from here, the next thing we just do is to substitute in those limits. So negative 8 pi, and it'll be a third cos cubed t, and that's going to be pi over 3, minus cos pi over 3 minus, and that will be 1/3 cos cubed pi minus cos pi. Right, so let's work that all out and see what we get. And that gives 9 pi, so I just typed it all in, and then I've got my calculator to work out the whole lot. So 9 pi will be the volume of water required to fill it. Moving on to part B, it says that the real golfer's bowl has a maximum diameter of 48 centimeters. Find the volume of water. So this is to do with scale factors. If I have a look at this little model here, this one has a diameter of 4 centimeters. So that means that the scale factor, let's write this down. So the scale factor that's going to take me from 4 centimeters to 48 centimeters is 12. So the scale factor is 12. Now what's the volume factor? Well, the volume factor is 12 cubed. Now 12 cubed, I'm not going to do that in my head. 12 cubed gives me a value of 1728. So to find the real volume, what I'm going to do is take 9 pi and multiply it by 1728. So times by 9 pi, and we get 15552 pi, and the volume of water then will be centimeters cubed. Now you could change that to a decimal, but there's no reason you couldn't leave your answer as an exact multiple of pi. So in that part of the question we used what we know about scale factors and volume factors as well. So you should now be able to do exercise 4D on pages 88 to 89 of the textbook. So I would say the main thing to take away from this section is if you have a scale factor, then the scale factor squared will give you the area factor. So if you have questions that talk about surface area of something, and the scale factor cubed is going to give you the volume factor.